Good morning, everyone. Myself, Sanjana Kumari. I am a student of Bengal College of Engineering and Technology from pursuing BTech Computer Science Engineering from second year. I feel honored to be the host of today's faculty development program organized by Entrepreneurship Development Cell Institute Innovation Cell. It's wonderful to see so many esteemed faculty members and guests gathered here, ready to share ideas and learn together. Now it's time pleasure to introduce our session chair, Dr. Divendu Mukherjee sir. We are honored to have his here to guide us through today's discussions. Now, moving on to our third session, the topic is algorithmic concepts for UAV and IoT assist a smart city. I am delighted to introduce our speaker, Dr. Sunirmal Khatwa, who serves as Associate Professor in the Department of Computer Science and Engineering at the University of Calcutta, specializing in cloud computing 1. Born in 1979, he has earned prestigious accolades including the Visvesvaraya Young Faculty Award from the Government of India 2018 and a Best Paper Award from IEEE ANTS 2015. His academic genre includes a PhD in Computer Science Engineering from Jadavpur University, where he also earned his ME with a gold medal won. With extensive teaching experience in subjects ranging from computer networks to cloud computing, Dr. Khatwa has made significant contribution to academic research, particularly in distributed and cloud computing, wireless and mobile computing, and Internet of Things. His professional experience includes roles at Tejas Networks and Wipro Technology, and he currently leads several research projects funded by organizations like DRDO and UGC. Please join me welcoming Dr. Sunirmal Khatwa as their share expertise on this topic. Over to you, sir. Thank you.
Thank you, Sanjana, for your nice introduction. So, how many faculties are there in this FTP? So, only we four are there, or okay? Okay, so let me first share my screen and then I will start. Is my presentation visible?
Yes, sir.
Okay. So, a very good morning to all of you. And let me start my topic that I will discuss today. So that is the algorithmic aspects for UAV and IoT assisted smart city. So today, basically, we are all are talking about the smart city and smart device and everything becomes smart. And two important players that make our city or make our equipment smart are the drones, or most scientifically we call it UAV, and some IoT devices. So basically, I will discuss a few of the works that are going on in my lab by two of my PhD students, Tathagata Rai and Pritam Kumar Shur. So they have just started their PhD this year, and they started working with a paper that was published in IEEE Transaction on Intelligent Transportation System in 2022. So I'll be happy if you participate in the discussion and contribute as well, so that we can also get some suggestions from you to go in the right directions to make our city smart. So basically, I will discuss about the drone-based parcel delivery. Now, why this is important in today's context? So let me first place the importance of doing this kind of research and where it goes. So I am showing a statistics from this is called modern intelligence system. So they have some statistical data from 2020 to 2023, and they have collected how many packets are delivered through drones, right? So before 2022, it was negligible, but you can see that each year the number of packets delivers are steadily increasing. And in 2023, the number of packets that are delivered through drones to your home approximate to 2 millions. And their projected market price for drone-based delivery, and they have projected that by 2023 or 29 or 2030, so it will reach around 2 billion US dollar. So the key players in that domain are basically Amazon, because we know that Amazon delivered the package most to your homes through couriers. So Amazon, along with the Amazon, in that drone-based delivery, the DHL, DJI, Zipline, they are also coming forward and take a active role in delivering the package to our home. And not only that, you know that in India, the Swiggy already started a project in South India to deliver their food items through the drones. So if I'm not wrong, within 1 or 2 years, you may see that some drone come to your homes with some food items you ordered in Swiggy. So obviously, these facts state that it's very important in today's world that in 2023, working on that drone-based parcel delivery, maybe it food or whatever the item is very important. But the fact is that majority of the contribution in that domain are from the industry, that Amazon, DSL, they are coming forward. But very less amount of research work is done in that part. So I find very few in that domain. And we get a very good paper in 2022 that published in the Transaction on Intelligent Transportation System. So I will take some part of this and how we contribute on top of it by my PhD students, and we will discuss about this. But before going to discuss about those things, so let me show you how Amazon are delivering those items through drones in Europe. So let me share one video so that you have some idea of how practical it is and how it is already going on in Europe. So this is a video from Amazon itself. Okay, so we have some idea of how these drones can be used to deliver the items to the doorsteps. So now let me just classify that delivering in the smart city and the delivering of the package in the rural area, how they differ. So I have shown these two from the OpenStreetMap. I have taken one from my university, that is Salt Lake in Sector 2. So this is the OpenStreetMap view of the Salt Lake Sector 2 places. These white lines are basically the road network. And if you look at the patterns of the road network, it mostly follows that Manhattan space. So that means if we force the drones to move only on top of the roads, the drone will follow the Manhattan space. Because in the city, in the smart city or in the city itself, the government will not allow to enter any of the drones to the residential complex kind of things. So that's dangerous. So there will be some security issues. So we can assume that the drone will be allowed. And not only that, in the city also, the buildings are very high rise. And the drones are not flying at a very higher distance. So therefore, we can assume that in a city, the drones will travel across the road. So we may assume that in a smart city, we had to follow the Manhattan traveling of the drones. But if you look at the rural area, so this is an OpenStreetMap of my village near Pascura. So you can see that mostly this is Euclidean space. So that means there is no so many high-rise buildings, and the height at which the drone flies. So that does not get any obstacle kind of things. So we can say that in rural area, the drone can travel in any of the direction if the government give the flying zone permit. So we can categorize these two, that when the drones are flying in a city, it will follow the Manhattan, and especially if it is a smart city or if it is a planned city. And in the rural area, we will fly in the Euclidean space. Now, now this generalization of this concept, because we don't know whether it is a city or whether it is a rural area when we are traveling. So we can take that region of interest where a number of package has to be delivered. So we call it a region of interest. So that can be generalized as a EM grid. And that generalization is done by Sorvelli and his team. And they have published this work in that title, Transaction on Intelligent Transportation System in 2022. So that area where the package has to be delivered, they considered like a grid of R number of rows and C number of columns. And they consider that this region may have both a village area and a city area. So we can say that a column K that separate these two regions. So we can say that 1 to k columns, you can see that starting from 1 to k columns, if you say in this part, so it says that 1 to k up to this column, considering all the roads, just follow the village area. That drone can travel in any of the directions, or we can say in the traveling in the Euclidean space. But the right side is basically a planned city that follow the Manhattan kind of things, following that road. So starting from k plus 1 up to that C, this follow the Manhattan space. And this kth column is basically the border. Now you may ask that generally the transition is not a straight line. It can be a zigzag, it can be any pattern. The significance of this grid is that the mathematical modeling becomes very easy with this kind of assumption. And when we will compare the results, we will run in the real geometrical space. And we have to say how close the result is in the real field. So while we design our algorithm, we will assume this kind of row by column grid, having separating the Euclidean space and the Manhattan space at a column at a vertical line, and then design our algorithm and apply that algorithm to the real field. And let's see how good it performs in the real environment. So that's why we can say that our Euclidean space is a matrix of one R cross K, and the Manhattan space is a matrix called 1 to R and K plus 1 to C, and the border is basically considering all the rows and only one column K. Now, this kind of generalization can be easily converted to full Euclidean or full Manhattan. So obviously, if you move that K, so for example, suppose we if we take this K fully to the C, that is whenever C equal to K or K equal to C, it becomes a fully Euclidean. Similarly, if we move k till 1, that means it becomes a fully Manhattan. So basically, we have considered this kind of EM grid as a general EM grid, or a fully Euclidean grid, or a fully Manhattan grid. Now, the thing is that for calculating the routes for the drones, we need to calculate the distance. Now let us consider that we need to find out the distance between two endpoints U and V. The first one, we consider that both reside in the Euclidean space. Both U and V fall in the Euclidean space. Then we can easily calculate its distance by the Euclidean function. And the second one is that if both the location, that is the sending and the receiving locations, both falls under the Manhattan space, then just add the number of rows and the number of columns, because you have to follow the horizontal and vertical movement in the Manhattans. So obviously, the distance function will be the total number of rows and the total number of columns between the sender and the receivers. So using that, we can calculate the Manhattan distance. But what happened in the general case? That, that the case when the sender is in Euclidean and the receiver is in the Manhattan, or the vice versa. It can be both. So how can we generalize that distance function? So we can calculate this distance in a general form by these equations, that when both falls under the Euclidean, use the Euclidean distance. When both falls under the Manhattan or the border, use the Manhattan distance. And these two cases, when one end is in the Euclidean and the other end is in the Manhattan, what do we need to do? So from triangle inequality, you can easily see that we have to map, we have to project the Manhattan space to the border and find the Euclidean distance. So if you see, suppose we want to find the distance between E and C. So clearly, the shortest distance will be just project C to the border and find the Euclidean distance. So that will be the minimal. No other path shorten or minimize the distance. So similarly, the distance, the shortest distance between E and D, can be found out just by projecting D to the border and find the Euclidean distance from that. So we can say that if in these two cases, we have to project to the H point in the border, follow the Euclidean from the source to H, and then follow Manhattan from H to V. If U is in the Euclidean and V is in the Manhattan. If it is a reverse, so just follow the Manhattan from U to H, because U falls in the Manhattan space, and then from H to V, follow the Euclidean distance. So in that way, we can provide a generic functions to find a distance, regardless whether it is in the Manhattan or Euclidean or a combination. Now, based on that, our objective, what is our problem? So along lots of problems are there, the security, meteorological data, that is the wind speed and all those things. One of the main important problem, how to find the routes, optimal routes, that should be followed by the drone. So route problem, that route finding problem of the drones is an important problem. And that has to be considered when the drone is capable of carrying only one package at a time, or the drone is capable of carrying multiple packages at a time. And also regarding that drone routing problem, we have used one term that is called last mile delivery. What does that mean by the last mile delivery? It says that generally, whenever we order a package on Amazon, it is coming from Bangalore, Hyderabad, or a longer distance, a few hundred kilometers away. So obviously, the drone will not carry your package from Bangalore or Hyderabad. So the package will come from those longer distance to a position in the region of interest. So somewhere we have to gather all the packets coming from Bangalore, Hyderabad, or all other places through a high-speed transportation system like train, aeroplane, buses, cab, like things. And we have to place them in one position called the delivery points. And from that delivery points, we will deliver it using the drone. Since from the source to end, only the last hop is delivered by the drones, it is called last mile delivery. And that is used because the drones can fly a maximum of 10 to 15 or maximum 20 kilometers range. So we will design the drone flying zone as a region of interest, and we have to find a position within that where we have to assemble all the package before it can be delivered to each of the users location. So we can define a mission. So we can define our route finding mission as a set of location of the users from where the package is ordered. and our objective to find a location U from where all this package in the mission has to be delivered. So if we consider this U as my delivery points where all the package will be assembled and then delivered to the drones, then we can define the cost functions for that mission using that U as the delivery point each, basically two times the sum of the distances to all the points V in that mission from U. Why this two? Because we have to deliver it and return back because our capacity is single. If it is a single capacity, each time I have to visit to the customer place, drop the package, and we have to return back. And if it is a multi-capacity, then we can take in one go, I can take multiples and follow a route and come back. So first one, I will discuss about the problems where the drones are small drones that can carry only one package at a time and deliver to one location. So since I have to deliver and return back, so that's why our cost function is two times the sum of the distances to the different locations within the mission from U. So that will be our cost function. And what is our objective? Our objective is to find U that minimize the cost function. So if it is a continuous space, we have to search in the infinite space. And if it is a EM grid, I have to, in a brute force, I have to search within R cross C so many places. Now, in a large area, if we consider that rows are the latitude and longitude concept, so it's huge. So brute force does not work to find this kind of optimal point. So we will use some geometrical concept, geometry. So to find those optimal point U star, which will minimize the total distance traveled by the drones. And while solving that problem, so it becomes an optimization problem. So while solving that optimization problem, we have to consider these three cases. The first case, says that the G is fully Euclidean. That means the drone is flying in the village itself. Or G is fully Manhattan. That is, the drone is flying in a planned smart city itself. Or it can be a general EM grid where a smart city and a Euclidean space converge. So within these three cases, I will analyze each of the cases and find algorithms to minimize, to find that optimal solution or find a near optimal solution to deliver the package to the users. So let me discuss about the first one. So in the first case, where G is fully Euclidean, so we consider this is our, for example, this location is our EM grid. The left side is Euclidean and the right side is Manhattan. And since we considered a full Euclidean, all the points, user locations falls under the Euclidean space. So there is no demands for the package from the Manhattan space. And since we considered the single capacity, we have to visit each of the location with one package and again have to return back. And let us consider this point is the delivery points we need to find. We don't know. The input is those points given. We have to find the delivery points where all the packages from Bangalore, Hyderabad, wherever it is, have to come and assembled at that point, and then the drone will pick off and deliver to each of the locations. So we need to find out these delivery points, and these are the delivery locations given as input to our algorithm. Now, clearly, it looks like that if we find the Euclidean coordinate, that is simple, the centroids, so that will minimize. So the first algorithm that I discussed is called the Global Euclidean Centroid or GEC algorithm, which simply find the coordinate wise, the mean value. So R is basically the X and C is basically the Y, the rows and the columns. So for all the rows present in that request, so take the mean of that, and for all the columns, take a mean of that. That position looks like at the center of that, and that should minimize. The good thing about this algorithm is that it runs in order of n. So if there are n number of delivery points to be delivered, so in a simple for loop, so we can calculate the for loop running for the n times, and we can find that centroid for that. So we are done with that. But unfortunately, that will not work because we know that the centroid minimize the sum of squared Euclidean distance. It does not necessarily minimize the sum of the distance. And our objective function, if you see our objective function not the square, it's basically the straightforward distances, sum of the distances. So obviously from that result, we can say that we cannot use centroid to optimally do that in the grid space. And not only that, this centroid may be a real number. So that again, we have to round it off to map to a grid point. That reduce it to the non-optimality. So we can say that this global Euclidean concept, Euclidean centroid concept, does not provide us the optimal solution to the problem. However, that study also shows that I am not going to discuss about this proof for that. So there's a proof. You can follow this paper and you can see that the proof that the approximation ratio of this algorithm in the general EM grid, that is whenever it run in the general EM grid, so its approximate ratio is 2. What does that mean? That means in the worst case, this algorithm runs with a 20% extra movement. So that's not bad, right? So only 20% extra distance that has to travel. But sometimes the 20% is also too high when you consider the cost of the drone's movement for the battery and all those things. So therefore, the better one is that we have to use the geometric median, because you know that geometric median, if we use instead of centroid, if we use the geometric median, that basically minimizes the sum of the straight line distances, not the square. So the centroid basically minimizes the square of the distances, but the geometric median minimizes the sum of the distance, which is our objective function. It is not the square of that. But the problem with geometric median is that the algorithm requires a more complex calculations for getting that geometric median compared to centroid. Because centroid is very easy. Just take the mean of the coordinates and we are done. So one such algorithm for finding that geometric median in that grid space can be used, that Whitfield's algorithm. So let me discuss about the Whitfield algorithm, how it calculates. Then we can see the complexity of that algorithm compared to that simplified GAC algorithm. So that Whitfield algorithm is basically it's basically an iterative algorithm. So running per iterations, and finally it may converge. It's not necessarily that you have to run continuously for long. So you can decide how many iterations to run, and as you increase the number of iterations, the accuracy of the algorithm also increase. And the good thing is that the distance functions, the Euclidean distance function, is convex in nature. So since it's a convex, there is no problem of a stuck in the local minima. So we know that in the convex functions, that issue is not there. So as we increase, after each iterations, we improve something. So basically, we can use the iteration, tune the iteration to compromise between the accuracy and the time needed to get that result. So in Whitfield algorithms, so they initialize with that centroid as we calculate. So first started with the centroid, and we need to tune it to the better result. The tuning they have provided by iterating that each time they update the U using these functions. So I'm not discussing in details about those things. So you can follow this Whitfield algorithm. So for their proofs and all those things, and they will terminate that they will converge or they will terminate this algorithm when the new value of that centroid is very close to the previous one. So we can define some parameter threshold. When the difference between the two successive loop is within that threshold, stop the algorithm, and the new value of this, it will provide a much better result than this. So for single capacity, if it is a fully Euclidean space, we can either use that simple Euclidean centroid algorithm, or we can use this Whitfield geometric median algorithms to improve the result further. The second one, the second case that I discussed here is a fully Manhattan. That is where all the points where I need to deliver my package falls under the right side of that, because the left side is considered as a Euclidean and the right side is the Manhattan. So if we assume that all the points fall under the Manhattan space, so then we can use a different thing. We cannot use the centroid, right? The centroid, if we take the centroid, but the centroid minimize the straight distances, so that will not work in the Manhattan, because in the Manhattan you are not allowed to move diagonally. Either you have to go horizontally and then go to vertically. So in Manhattan space, we need to find the coordinate-wise median. So that's a very simple thing, because if in a Manhattan space, If we use the coordinate-wise Manhattan, that will minimize the sum of the distances in the Manhattan space. So we will get the optimal result if all the points falls in the Manhattan space itself. So what we will do? So given all the points, just find that coordinate-wise median as the median of the rows. Take all the rows, sort it in the ascending order, and take the median value only for the rows. Similarly, take all the columns, sort them, and then take the median of that column itself. And combinedly, it will give you the delivery points. And that will minimize the total Manhattan distance to be covered in the Manhattan space itself. Now, if it's a general EM grade, so obviously this solution will not provide us a optimal solution. But that also have been proven, and the proof is given in that paper. So you can see that its approximation ratio is order of 2, even though it is also running in order of n. And by root 2, you can say that in the worst case, so hardly it will increase 11 or 12 kind of 12% of extra distance to be covered, which is much less compared to the 20% as in the case of the Euclidean space. So if you consider this Manhattan and put it into the normal EM grid, so it will provide much more closer result to the optimal one, because here the approximation ratio is root 2 and the previous one the approximation ratio is 2. Well, in the next case, the last case, that is in the case 3, in the case 3, we are considering that it's a general EM gate, that not necessarily that all the points fall in the Euclidean space or all the points falls in the Manhattan space. It can happen that some of the points fall in the Manhattan and some other points fall in the Euclidean. Now, the majority can be in any of the cases. In one case, the majority is if you see in the first case, the majority of the points falls in the Euclidean space. And in the second one, majority of the points falls under the Manhattan space. So we can assume that if majority of the points falls in the Euclidean space, the optimal deployment point may fall in the Euclidean space. But that may not be true always, because the Manhattan points may be in a far distance from the border, right? But we can take that assumption that if it is there, what will be the result? Or we can also take the assumption that if majority of the points falls in the Manhattan, we can assume that the optimal deployment point should belongs in the Manhattan space. Now, using these assumptions, we can provide good algorithms to find the optimal deployment point. The first algorithm is called Euclidean centroid by projecting the Manhattan to the border, right? What does that mean? In that case, since I assume that it is there, so obviously to reach it, we have to go to that border and then follow the straight line. So that will optimize the distance that we have already seen in the previous discussion. No other movement can minimize that total distance. Now, since we have to follow this, we can project those points to the border. So just project these Manhattan points, each of the Manhattan points projected to the border, and then we can assume that all the points falls under the Euclidean space. Then apply the first algorithm, that assuming all the points are the Euclidean space, then find the centroid or the geometric median to find the optimal one. So if you see, the algorithm is that. So this one is basically projecting all the Manhattan points to the border, because the border is at K, right? So for all the points that are under the Manhattans, so their column number will be K. And for all the points in the Euclidean, we have to take their actual column number to calculate the columns. But for all of them, the row number are unchanged. So for all U belongs to the full mission, we will take the actual rows, and for the column, we will separate them. One for the points that falls under the Euclidean, and the other for the columns that fall under the Manhattan. For the points that fall under the Euclidean, take the actual column number, and for the points that fall under the Manhattan, take K for the column number. That means for all of them, they comes under that border. And then follow this normal centroid, if I want to use a centroid, or then use this iterative methods to tune it to find a more accurate results for that Euclidean space. While in the last one, you can see, since the majority of the points falls under the Manhattan space, we can assume that it will be in the Manhattan. So, so in that case, I don't know where the Manhattan point will be there. If the Manhattan point is there, then all the Euclidean point has to meet at that point at the border and then follow it. But this point can reside in any of the points, in any of the row. So then we have to perform a brute force kind of search here. So for all the points I from 1 to R, so take this Manhattan coordinates, that whatever we discussed about in the previous one, the Manhattan distance minimization. So assuming that the global point is at point I, then we can find the coordinate wise Manhattan mean to find this. And for all the values, just calculate this cost and take the minimum one. So that will give you the optimal result if the delivery points falls in the Manhattan space. So obviously, this will not give the accurate result if the actual points falls in the Manhattan and we assume it to be the Euclidean or the vice versa. So in that case, the result will be slightly deviated. But anyway, we can consider those things as a heuristics, and the experimental result shows a promising result that in the real environment, if we use a brute force search, whatever the result we get, this result is also very close to the optimal one. Now, all those discussions are related to a single capacity, that the drone has a single, at a go, it can take only one package, go to the delivery point, drop it, and come back. But nowadays, we are having a high capacity drones. So at one go, they can take multiple package and go to the air. So if they have multiple capacity, if they have if so if they have multiple capacity, in that case, it is not needed to go there and return back. Rather, if its capacity is 4, it can go there, put one package, then visit this, put the second package, then visit there, put the third package, then visit here, put the fourth package, and then come back. Right? So in that case, given the same mission with the capacity K or with the capacity P, so we need to find the tours, basically find the tours, and our cost function minimize the tour length, not the distance to each of the points, right? So we have to find the multiple tours. So we can say this is tour 1, this can be considered as a tour 1, this can be considered as tour 2, tour 3, like that. So we can have k number of tour, and each of the tour has different length, and we have to find point. So we have to find this is the delivery point. So we have to gather all the package from the high-speed transportation systems, and then that minimize the total tour length. So if there are nc number of tour length, which point you minimize this cost function. So for single capacity, the cost function was the distance, sum of the distance to each of the points. Here we have to find the tours and have to find the length of the tours, and that total length has to be minimized in multi-capacity case. So let us see how we can do that. So obviously, one basic concept is that we have to cluster the nodes. If there are n number of nodes given, so basically we have to cluster it. So the clustering, by clustering, the k-means clustering is a very good approach to cluster it. But the problem is that in case of k-means clustering, that will find k number of clusters whose inter-cluster distance is minimized and the inter-cluster distance are maximized. But that is not our objective. Here, I have to find a cluster where the maximum number of nodes will not be exceeded by the capacity of the drone. So we have to construct P by K cluster. If P is the total number of points where we need to deliver. So we have to set the K for the K means as the P by K. If K is the capacity of the cluster, right? So we will divide P by K to get how many clusters to be formed. And using that parameter, we can run the K-means clustering. Now, if we just run the K-means clustering with P by K, it will cluster it, but it can happen that in some of the clusters have more than K number of nodes. So we modify this K-means clustering called the K-means constraint. So we have designed a K-mean constraint cluster that while it is forming the cluster, whenever the number of nodes in the cluster becomes k, it will no longer accept a new. So it will return the distance function as infinity to each of the points. So that constraint will enforce that none of the cluster formed have more than k number of nodes. Or we can say that it will divide exactly k node clusters, probably the last one will have less than k number of nodes in the cluster, but it will guarantee that each of the cluster has k, and our the capacity of the drone is k. So that can cover at one go the drone can cover all the points within the cluster. So first we will form this kind of clustering using a modified k-means clustering called the k-means constraint, and then we will find out the points. Then we will find out the centroid of the cluster. For example, one cluster is formed here. This is the centroid of that cluster. This is another centroid. This is another centroid. So we will find the centroid of the cluster formed, and and we can assume that the drone has to travel to the center of that cluster itself. So we tried to minimize the center. So we find the center of the centroids, or the centroid of the centroids, basically we find out that, and we consider that to be the initial delivery points, dp. But obviously, that is not a good idea, because we will never travel to the centroid of the cluster. We have to travel to the roots. But approximately, as the centroid is very close to the points, this is a good approximation that if we take the centroid of the centroids of the clusters, so that may minimize the total tool length. But with that, we will again further tune that delivery points later. So what it does is that, considering that delivery points and the elements in that cluster, for each of the cluster, we perform a TSP. That starting from that, if I want to follow a tour to cover all the points, so just run a TSP for a cluster starting from that U prime, that is the centroid, right? And if the number of nodes in the cluster is much more high, that is, if p by k is very large, in that case, what we does, we use approximate TCP. The approximate TCP is a Christopher algorithm. So whenever p by k is very less, we use the normal TCP to find that route, and whenever the p by k is very high, we use the Christopher algorithm to find the routes with a very quick times using the polynomial approximation. And the approximation ratio of the Christopher algorithm is that it's 3 by 2, right? So that will also provide a good solution for that. And for that we will calculate the entry and exit point. That ultimately, for covering that cluster, we have to go to the entry point of that, and again finally have to come back. So ultimately, for each of that cluster tour, we will find the entry and exit point for each of the tours, and using that entry and exit point, find the centroid. So that will give you a much better result than just the centroid of the centroid values. So that one can be a good idea for if all the points falls in the Euclidean space, and we have a capacity of k. Now, if it is a fully Manhattan space, then we can follow the similar things, but when we are forming the tour within the cluster, we have to follow the Manhattan tour. So using the similar approach, we can use the fully Manhattan space as well. Now, in a general case, that is, some of the points fall in the Euclidean and some of the points fall in the Manhattan. So what we does is that we will separately find the tours for the Euclideans, and we will find the tours separately for the Manhattan. So construct the clusters separately for the Euclidean points and separately for the Manhattan points. And then for each of them, find the delivery points using the previous algorithm for the Euclidean space itself, for the Manhattan space itself. Now find the tours, construct the TSP considering that current delivery points. And we have to compare the result. So we have to take either the delivery points in the Euclidean or the delivery point in the Manhattan, which one minimizes that value. So that can be considered as a good heuristics to find the total sum of the distances covered by the tools in multi-capacity, general, EM grid as well. So so this one is the second part. So till now I discussed the two part. The first part that considered that there is a single capacity. It can be a fully Euclidean, it can be a fully Manhattan, or it can be a general. The second part that I discussed is multi-capacity. And again, I have considered those three cases for multi-capacity, that if it is a fully Euclidean, or if it is a fully Manhattan, or, or in case of a general EM grid. Now, now the thing is that in a normal city, in the normal city that are not like exactly this kind of grid, we can assume that a city, a smart city will allow your drone to travel in any of the locations for those registered drone itself. The drones from the Amazon will be allowed to enter your residence and drop your package. So obviously, the smart city has a detection kind of mechanism, so that can detect and allow some of the drones to enter and some others not. So in that case, we will not follow the Euclidean or Manhattan. Rather, we can say that it's a general space with some obstacle. So obviously, it will fly in any of the locations, but if there is a building, large building, it has to avoid that obstacle. So basically, the last thing that I will discuss is that the zone routing problems in the presence of obstacles, we have to find the optimal routes. So for that, we are considering that given T as a set of targets from where the package request come, and O are the obstacles. O are the obstacles represented by the polygons, right? So each of the obstacle, if we consider these are the obstacles, so these are the corner points of the polygons. So each of the polygons can be represented, each of the obstacle can be represented by such a polygonal structures. And the Ci is basically denoting the corner point of each of the obstacle. Now we define DE. Already in the first slide, I defined the distance. Now I define the distance for the two different categories. One, when there is no obstacle, we call it DE, Euclidean distance. And the other, when we define the distance between AB in the presence of obstacle, we call it DO. So obviously the DO is exactly equal to DE if they have a line of sight visibility. That is, if there is no obstacle in between. Otherwise, the DO value will be greater than the DE value between A and B. Now, with that definition of the variables or different symbols, our problems can be classified into these two. The first one is a single capacity drone path planning in the presence of obstacle, and the second one is multi-capacity drone path planning in the presence of obstacle. So we can formally define is that given a region of interest R, so here the region of interest is not a EM grid, it's any general region of interest, but having a set of obstacles O, excuse me, within that R and a set of targets where the package has to be delivered, we need to find out that delivery point U that minimize the sum of DO, not the DE. That the distance to those targets in the presence of obstacles is the distance. That distance function has to be minimized in that first case. And in the second case, we need to minimize the tools, not just the distance. I have to find the multiple tools and which one minimize the total length of the tools. We have to find this. So let us discuss these two problems separately. The first one, that I have a single capacity of the drones and I need to find out the total distance, the sum of the total distance DO that needs to be minimized instead of D. If it is a simple DE, then it becomes the same problems of the Euclidean space problem. Now, since there is some buildings, you can see those are the sum of the buildings. So we have to find, minimize the DO distance. For that, what we do, initially, the algorithm we propose is that it's a very simple one. We consider there is no obstacle, no building. So as usual, considering the fully Euclidean space, find the centroid. So suppose this U prime is the centroid we get. And then generate or construct a graph. When we construct the graph, how we construct this? We take this centroid. When we construct, we take this centroid, all the delivery points T, and all the corner points of the obstacles. For each of the obstacles, they are polygons. They have some corner points. So taking those corner points, delivery points, and the current centroid, create a graph. These will be the vertices of the graph. And what will be the edge? Within that, for any two combination of the vertices within that set of vertices, if they have directly visibility, that is, there is no obstacle within these 2 points, then we add this to the edge of the graph. So in that way, within the constructed graph, so clearly each of the edge does not have any obstacles. So that can be visited using Euclidean functions. So their weight will be the Euclidean distance between Vi and Vj. Once I form this graph, we need to find the single source shortest path distance starting from that Euclidean distance. So we get this uh, estimated delivery points. So from that point, find the route that avoid obstacles to reach to that delivery points. So obviously, since the graph is constructed where each of the edge does not have any obstacles, so within that path, it does not have any obstacle. And we are taking the shortest path from that centroid to the points. So after getting those shortest path, find a set of points which first meet a corner points. For example, this one, this one. So we take all those points and find the geometric median of those points to update this value, because previously whatever you consider may not be the optimal, but after finding this, ultimately to reach to that destination we have to go to that corner point, then I have to follow the path. So now our objective is that considering only the corner points, find the geometric median that will update the delivery points to a different positions. So maybe that's a different position there. So that way we can tune it. And if we want to follow the tours, we will use all the similar concept, not only the path, so that will find some tours that avoid the obstacles and further minimize the total length of the tours. So I think with that, I will stop. And if there is any questions, so I can take those questions here. So, Shantanu? Or,
Hello.
yeah.
Thank you, sir. So, on behalf of the organizing committee, I am delighted to extend our sincere gratitude to our distinguished speaker, Dr. Sunirmal Khatwa, sir, for sharing his valuable insight with us. Hopefully, all the participants enjoyed the session and learned lots from you, sir. And sir, I have some questions that the audience has already shared throughout this session. So, with your permission, can I ask?
Sure, sure.
So the first question is, what is the use of L1 and L2 norms in ML?
Mm, pardon me? Your voice is...
Sir, what? Okay. What is the use of L1 and L2 norms in ML, machine learning?
But this is a questions from something else. Whatever I discuss, it's not. So
Okay.
it's better to
Actually,
take the questions. Yeah.
okay. Actually, some of the audience has asked this question. Okay, no issue,
Yeah,
sir.
sure. But whenever I discuss about the machine learning, it's better to ask these questions.
Okay, fine, sir. Okay, sir, the next question is, how do your algorithm manage the real-time processing and storage challenges associated with such
Your
large-scale
voice is
data?
breaking. So can you send the text here in the chat box?
Okay, that will be fine. Okay, sir, just wait for a minute. Just wait for a minute, sir.
Yeah, sure.
Sir, please check the chat box once.
Yeah. So real-time processing and storage challenge associated with such large scale data. So that's why I told you that we are not considering a centralized, it's a distributed algorithm. So for each of the local area we are finding, so it's not that Amazon will process this for the whole India kind of things. So in a local area of small region of interest, so obviously the number of points will be less, so where we can store it, right? So for example, only for the Salt Lake area, so at a particular point of times, the total number of packets that comes is not so huge so that I have a large kiosk. But for each of the area, they have a separate kind of region of interest. So small storage that call the deployment points. So they will have some buildings to store it properly. And in the real also, if you see the big basket and all those things, they also have some kind of kiosk where they put all the points before it will be delivered to that. So the same concept in the existing non-drone based delivery, the managing of the storage and processing is the same thing. But regarding the processing part, since I am dividing the area into the region of interest and each of the region of interest running in parallel, so the processing time is not more. And already I show you that all those algorithms are order of n. So since it is order of n and the n within that small area is very less, it can be easily managed.
Okay. Okay, sir. Thank you once again. I have no more questions. Okay, so this was the last question. So thank you once again, and hopefully we will look forward more session with you in near future. And thank you for your time and effort. Thank you, sir.
And for the machine learning questions, so since
Yes.
this discussion is not in machine learning, I'm not going to discuss. But you can share my mail ID. I will answer through mail to that.
Okay, sir. Okay, fine, sir. Fine, fine, fine. Thank you, sir. Thank you. Thank you all the participants. Thank you.
Fine.